Okay, thank you for the introduction, and thank you all for coming to my talk. So I'll be presenting our work on discrete elastic rods. And an elastic rod is a long, thin piece of elastic material, such as this string you see here. And in this experiment, you see this knotted piece of string where we twist the ends of it, and in response to this, the shape kind of bends and buckles out of the plane and forms these interesting shapes. So as you can see in the simulation right above the experiment, using our discrete rod model, we're able to reproduce this interesting kind of interaction between the bending and the twisting of the rod. So that's what I'm going to be talking about today. So we base our work on the Kirchhoff rod model, which consists of a curve called the center line of the rod, and also an adapted material frame, which describes the orientation of the actual elastic material around the center line of the rod. And what I mean by adapted is that the third vector of this orthonormal frame is always along the tangent of the rod. And this animation just shows how this orthonormal frame follows the elastic material around the center line. So the Kirchhoff rod model also assigns an elastic energy to every configuration of the rod. And this consists of two components. The first is based on the curvature of the rod, and this measures how the center line bends, essentially. The second component measures how the elastic material twists about the center line, and this essentially measures the speed of rotation of this frame as we move along this center line. So we combine these two measures of strain to arrive at the standard Kirchhoff energy for the rod, consisting of a bending and a twisting part. Now, traditionally, curvature is relatively straightforward to discretize. And twist is somewhat harder to capture neatly and easily. So that's going to be one of the focuses in this talk, is how we can come up with a simple formulation for the twist. So to evaluate the terms in this energy you just saw, we have to be able to describe any given configuration of the elastic rod. That is, we have to basically come up with a set of coordinates to use that represent this adapted framed curve. Once we come up with a set of coordinates we're going to use, essentially everything else follows. We're going to be able to evaluate the energy you saw, and from that take its gradient to evaluate the forces necessary for time stepping during simulations. So this is where our main contributions come in. We use a discrete curve and angle representation, which is going to lead to a very simple formulation for the twist, while also having the benefit of representing the center line explicitly, and I'll talk more about that in a bit. We base our work on smooth geometric concepts such as parallel transport, and we discretize this, and this foundation is going to allow us to make some observations about the interaction of bending and twisting. We also use the quasi-static material frame assumption, which says that the material frame evolves quasi-statically in time as the center line of the rod moves. And this is going to lead to a very simple and fast implementation, such that we're going to be able to run simulations in real time. So before I get into our approach, let's take a look at some previous work. So this class of work is based on a reduced coordinate formulation. And essentially the idea here is that we can build up any configuration for an elastic rod using reduced coordinates such as joint angles or curvature and twist degrees of freedom. And essentially this represents the center line implicitly, because we need to start from one end and integrate out these coordinates to recover the actual position of the center line. So as we see in this animation, oftentimes rods undergo complex collisions and self-collisions. So in this case, it's desirable to actually represent the center line explicitly, because that's going to be easier for collision detection and response to handle. So one type of approach that achieves this, having an explicit center line, is constraint methods, where we represent both the center line explicitly and the material frame explicitly, such as with quaternions, for example. And then we couple these two together to enforce the fact that the material frame has to be adapted to the center line. That is, its third vector has to lie along the tangent. That's enforced with a constraint. So there are some trade-offs between these two approaches. The first, obviously, is the constraint methods are able to handle collisions much more easily because they represent the center line explicitly. However, the formulation of the twist becomes somewhat more complicated because now we have to write everything in terms of quaternions, for example, whereas reduced coordinates kind of capture them naturally. So it seems like we're able to trade off one nice thing for another, but our goal in this talk is going to be to come up with a formulation that has both of these nice features. So the foundation for this is going to be the curve and angle representation, which has the explicit center line, which makes collision detection easy, and also is going to lead to a very simple formulation for the twist. So let's take a closer look at this representation. First in the smooth setting, and then we're going to transition to the discrete setting. So first we start with an explicit center line, in this case just the curve gamma. And along each point on the center line we're going to assign a reference frame. And recall that one of our goals is to come up with a simple formulation for the twist. And we're going to see how that's going to be achieved by using the twist-free frame as the reference frame. Now once we have this reference frame, we can describe the material frame at each point using just a single angle that says how much do we rotate this reference frame about the tangent to describe the material frame. So in the continuous setting, the coordinates are this curve gamma and the angle theta at each point along the curve. So now the interesting part of this is how do we actually construct this twist-free reference frame. So the way this works is we can assign it arbitrarily at one end of the rod, any orientation we choose, and then the requirements that it stay twist-free and adapted to the curve uniquely define it everywhere else, as seen here. So these two requirements, the twist-free requirement and the adapted frame requirement, define parallel transport, which is what you just saw, taking the frame at one end and mapping it in a twist-free way everywhere else along the rod. And this is defined as simply rotating the frame about the binormal at each point to map it to the next point. So this is parallel transport. And now we're in a position to actually evaluate the energy, the necessary terms, the curvature and the twist in the energy we wrote down. So the curvature we can just write in terms of the center line. And the twist, as you can see here, takes on this very simple form. It's just the arc length derivative of the angle theta. So now an interesting question comes up actually, which is, well, we write the curvature entirely in terms of the center line, and we write the twist entirely in terms of this angle theta. So how do these two terms interact? Essentially what we're asking is, well, the bending forces, we know that they're just going to try to reduce the curvature, that is, straighten out the center line. So what are the twisting forces going to do? And in order to answer this question, we're going to have to look at how this angle theta changes as we vary the center line. So to do that, we're going to look at this following experiment, where we take a straight piece of elastic rod and we twist both ends and we hold these ends fixed. And now we're going to look at the twist-free frame and how that changes as we change the center line. So here we see the twist-free frame. Obviously for a straight rod, it's just going to be the same everywhere. But now if we vary the center line a little bit, we're going to see that we get actually a rotation of the frame. Now if we vary the center line even more, we're going to end up with a larger rotation. So we see that changing the center line actually changes the angle theta. We're holding the material frame fixed, and the twist-free frame rotates, so the angle theta is going to change. So now we can ask the question of, okay, what are the twisting forces going to do? They're going to try to align the twist-free frame to the material frame. As you can see here, as we move the center line, we see this rotation happening. The angle is being reduced between the material frame and the twist-free frame. And it can be shown that the change in angle is related to the variation we introduce, this delta x, and also the curvature binormal of the rod. And this fact we're going to use later on in the discrete setting, so keep it in mind that it's related to the curvature binormal of the rod. So now we're in a position to answer the question we had originally, which is how do bending and twisting interact? And we see that both depend on the shape of the center line. So as I mentioned before, the bending force is essentially just going to move the center line towards a straighter curve. And the twisting force is going to act in a way to align the twist-free and the material frames. So this is where the interaction between these two come in. And this is why you normally see these helical shapes forming in elastic rods. So before we move on to the discrete setting, I want to introduce the quasi-static material frame postulation. We arrive at that by asking the question of what is the speed of twist waves along the rod? The answer is, well, it depends on the rotational inertia of the cross-section. And as we make the rod thinner and thinner, this rotational inertia essentially goes to zero. So in this case, twist propagates instantly along the rod. And in this animation, we see the limit of this process as twist waves propagate instantly. That is, as we twist one end of the rod, the number of turns that the material frame makes for any given length of the rod is going to be a constant. So again, in the thin rod limit, that is, as the cross-section vanishes, twist propagates instantly. And this in particular means that it's going to be wasteful in terms of computation to resolve all these very fast moving twist waves if we're going to simulate thin rods. So that's why we proposed a quasi-static material frame. We just update it in a quasi-static manner, and we're going to see later on how we actually enforce this requirement during the simulation. So now we're at a point where we can move over to the discrete setting. The way we're going to do this is by building up all the structure you just saw from discrete building blocks. Namely, we're going to introduce the discrete curve and angle representation. We're going to see the discrete version of parallel transport, and that's going to lead to discrete notions of twist and curvature. So first, the discrete curve and angle representation. Again, we start with an explicit center line, which in this case is just a sequence of vertices connected by straight edges. Next thing we need is a reference frame. And here the question is, well, where do we assign the reference frame? We can either assign them to edges or to vertices. And we answer this question by saying that tangent vectors can be uniquely defined at edges, just as pointing along the edge, whereas they can't be uniquely defined at vertices. So we assign frames to edges because of this. And again, we're going to assign the reference frame to be the twist-free frame, now in the discrete case. So once we have this, we can again use a single angle per edge to describe the material frame orientation relative to this reference frame. So here you see the coordinates we use, just the vertex positions and the material frame angles per edge. So again, let's see how we define the twist-free reference frame in the discrete case. And this is going to follow the same thing we did in the continuous case. Namely, we assign some arbitrary orientation for it at one end of the rod, and then our requirements are going to be able to uniquely define it everywhere else along the rod. So at each edge, we have a reference frame. So the requirements again are no twist about the tangent, and the frame has to stay adapted. And this defines discrete parallel transport, Along an edge, we just translate the frame because we're not allowed to twist about the tangent. And at a vertex, we have to rotate it to align it to the next edge. So we rotate that about the binormal. And this defines discrete parallel transport. So now again, using our discrete set of coordinates, we're able to evaluate the discrete version of the energy. And we do this by taking the continuous quantity, in this case the arc length derivative of the angle, and replacing it by this difference of angles between two consecutive edges. And again, you see that the twisting energy takes on this very simple form. Now, for the curvature, we have to ask the question of what definition of curvature we're going to use. And to answer this question, we're going to make use of what we learned in the continuous setting, namely that the change in this angle between the twist-free frame and the reference frame is going to be related to the curvature binormal of the curve. So we're going to do the same experiment in the discrete case, compute this change in angle, and that's going to tell us, that's going to give us a definition for the curvature. So here we have a discrete curve where we're again holding the material frame fixed at each end. And again, when it's straight, the reference frame is just the same everywhere along the curve. Now again, if we introduce some variation, we see here, we're going to end up with a rotation again. And of course, depending on what this variation is, we get a larger change in the angle. So now again, the goal is to compute what the change in the angle is given how I vary the curve. And we show in the paper that this is the resulting expression. Now, how does this help us? Well, when we compare it to the result from the continuous case, we can identify this portion of the resulting change in the angle with simply the arc length derivative of the variation we introduce in the curve. So we can identify the rest with the continuous quantity, the curvature binormal. And comparing these two quantities, we end up with the following expression for the curvature, which is just related to the turning angle at a vertex. So now, essentially, we have everything we need in the discrete case to run simulations. So now, next we have to see how to enforce the quasi-static material frame postulation while we're actually running simulations. And in order to do this, updating the material frame quasi-statically, we can enforce that by requiring at each time step of the simulation that the energy has to be at a minimum with respect to each of the theta variables. That is, with respect to each of the material frame orientation angles. So this gives us n equations and n unknowns, which we solve at every time step. And as a result of this, computation is going to be greatly simplified. First, because as I mentioned before, we don't have to take time steps small enough to resolve these very fast-moving twist waves. So we can take larger time steps. And second, this update actually requires less computation because we don't need to update the theta variables based on their momentum. We can just use this formula to actually get immediately what the theta variables are. Now, as a result of this, twist is always going to be uniform for isotropic rods. That is, it's going to be spread out equally along the length of the rod. However, for anisotropic rods, as we see here, this is no longer true. The twist can get more compressed into one region of the rod. And this is even more obvious for rods with some natural curvature. As we see here, the twist is concentrated entirely on the left until it makes these kind of discrete jumps over to the right side of the rod. And this is all done using the quasi-static material frame postulation. Okay, so let's take a look at how we combine all these components that you just saw and how we put everything together to actually run the simulations. So the first thing we have to do at each time step is update the reference frame, and this is done using parallel transport. Next, once we have the reference frame, we have to enforce the quasi-static material frame assumption, and we just enforce this using the system of equations that you saw before. And now we can compute forces on the center line. And these are given by the gradient of the elastic energy, as well as any external forces that we have in the system, such as gravity, damping, or whatever. And now we can update the center line positions. That is, we can time step the center line using any time stepping scheme that we choose. So we evaluated this method and tested its convergence using two examples. In the first case, we took a long straight piece of elastic rod, again twisted both ends, and as we move the ends together, a helical shape forms in the center. And what we plot in this graph on the top is, in red, is the envelope of this helix, the amplitude of the envelope of this helix. And as we see, under refinement, we converged to this limit predicted by the theory. The second one is also, we take a long straight piece of rod, twist the ends, and then glue the ends back together. And depending on the amount of twist we introduce before gluing the ends together, the rod either stays circular in the plane or buckles out of the plane. And this curve is shown on the rod, is shown on the graph of where this critical twist happens. And as we see in the simulations we ran, plotted using blue and purple dots, we again match this result predicted by theory. So in this next example, we take just a normal slinky, and we flatten it out along its cross section. Now as we move the ends back together, you see that it doesn't go back to its original rest configuration. It actually forms two helices connected in the middle of opposite chirality. And when we run a discrete simulation using the same rest shape as the slinky, we see that we're able to reproduce this result as well and get these two helices forming. So in this final experiment, what we see is, in this case, the elastic rod is actually the spring that this mass is attached to. And as we introduce some slight amplitude to this motion, we see that the mass at the end goes from purely bobbing up and down to purely twisting side to side. And in this discrete simulation, using a very coarse sampling of 31 vertices, we see that we're able to reproduce this interplay between the bending, or between the bobbing and the twisting modes. So I'd like to leave you with some final thoughts that we discuss in the paper. And the first is we describe how to handle the cases of anisotropic bending, that is when we have a ribbon that's essentially flatter in one direction, so it's harder to bend in that direction than another, and natural curvature, when the rest shape of the rod is naturally not straight, so curved. Second is, I didn't discuss extensibility of the rod. So we can have extensible rods just by, for example, introducing a spring energy per edge, or we can enforce an inextensibility constraint per edge. And we discussed both in the paper. We also need rigid body coupling for the example you saw before. We have to attach this mass to the end of the spring. And we discuss a method for doing that in our paper as well. And the final one is, well, once we're able to connect rods and rigid bodies, we can form interesting shapes, such as this tree that has T-junctions, where the branches of the tree meet. So I'd like to thank the following people, and I'd like to thank all of you for listening. I can answer any questions you have.
Well, we started a little late and kind of ran a little bit over there, if my times are correct. But we're going to have a couple questions anyway. So if you would like to start going to the mic to ask questions, please state your name and affiliation before you ask the question. I'm going to go ahead and ask the first question. This question was suggested to me by Sunil Hadab from Adobe. Thanks, Sunil. So although you already have some energy dissipation from your fast projection method, do you see an advantage of adding some true internal dampening to the model, damping, and how would you go about incorporating that?
Yeah, so for damping, it's obviously, if we want to kind of reduce the amount of wiggling, for example, then we can add, we actually have an implementation of air drag, for example, that just damps based on velocities of vertices. But we can also add a kind of stiffness damping that's proportional. For example, in the case of bending, it could be proportional to the velocity of the turning angle. And that would damp just the component of the motion that's along the bending direction, essentially, and leave rigid body motion intact. So if the entire rod is just moving as a rigid body, it wouldn't damp that kind of motion.
Go ahead.
Christian Lessig, University of Toronto. I've got a question on the parallel transport. So did you develop it for your paper, or did you just take it out of the literature? And is the parallel transport in the discrete case uniquely defined, or are there multiple options to discretize it?
So we didn't find any literature, or we don't know of any literature that defines uniquely parallel transport in the discrete case. So we developed it for our paper, and essentially what discrete parallel transport is, the way we defined it, is if you look at the tangent along the rod, this gives a single point along the surface of a sphere. And the way our discrete parallel transport works is we connect these points with geodesics on the sphere, and we use the standard continuous parallel transport along these geodesics.
Okay, thank you.
Okay, so we'll just move on to the next speaker. Thank you very much.
Thanks.